Okay, gang. Well, so I'm going to try something different this time. I'm re-recording my Stellar Evolution, The Life and Death of a Star. Um, this time I'm using voice narration, and then I'll try and publish that as a YouTube, and then maybe that'll be a little easier for you guys in the class to watch this at a time that's convenient for you. So I'm just going to go ahead and then we'll arrange later by email exactly how you can contact me and talk to me about questions and so forth if you have them. Okay, so we're doing this week the evolution of stars, the life and death of a star. This is a little summary of what we're going to talk about. We're going to look at how low mass stars evolve, high mass stars evolve, and then something I'm going to do that's a little different than the textbook. We'll talk about how low mass stars are really more properly divided into low and medium mass stars. Okay, so the first thing is that stars are always born in star clusters. I think we talked about that when we did our lecture on star formation. Why star clusters? Because we need enough mass to get enough gravity to make stars. You're just not going to have the conditions be right for the formation of one single star out in the middle of nowhere in our galaxy. The gas densities are too low, and the environment with other stars shining on it is not right. So what we need for gravity is we need low temperatures, so the gas doesn't want to just wander away. Remember what low temperature means. It means slow velocity for the individual particles. And since gravity is very weak in these low density environments, then you need that kind of help. So by low temperatures, we mean something like 30 degrees Kelvin above absolute zero. Way, way colder than what you might think of as cold here on Earth. We also require dust, so dust helps to be a little landing pad for atoms to land on, like hydrogen and carbon and oxygen, and then after they land on the dust, then the dust can help those atoms come together and become molecules. They may drift off again, and then collisions between molecules actually excite the internal motions of the molecule, which then de-excite, giving off infrared photons. And in a very low density gas like this, those infrared photons are very likely to just escape. So the net result is they're a coolant. They take away the velocity energy of the gas and therefore helps gravity to pull things all together. So there's an open star cluster, a pretty rich one. I think this one is M11, the wild duck cluster. Notice how many of the stars are blue. That's main sequence stars. They're just beginning their hydrogen burning. I see a few red stars here. Those might be early red giants. They look a little too bright to be red dwarfs. Red dwarfs are the lowest luminosity stars, and they're quite a bit less luminous than main sequence stars that are white or bluish white. So I'm guessing these are actually high mass stars that have already evolved off. That's the story that we're going to fill in as we go along. So these star clusters inherit the internal motions of the gas, and therefore you should think of them not as a static thing, which they may look like to you during your whole life. I doubt that you'll see any change in the positions of these stars. However, if you age over thousands of years, you'll see that they wander, and if you speed them up to a time that's more appropriate for the evolution of star clusters, you'll see that they actually it's like a kind of a crazy square dance, a bit of a random crazy square dance. And so the stars pick up energy. Some of them will actually evaporate at the expense of others who get in closer, and eventually just about all the stars will evaporate, but you may make some tight binaries in the process of losing energy. So the clusters get wider and more widely diffuse. And then eventually we don't call them a star cluster, we would call them an association. So prominent associations in the sky is the Alpha Persei association, made up of the bright stars near Alpha Persei. And then the most famous one would be the Big Dipper. So the Big Dipper stars are actually all members of a single star cluster, about 75 light years away. And the interesting thing about that cluster is that that association, as it expands, the boundary of it is already past the location of the sun right here. So we can identify, using velocity measurements, we can identify members of that old cluster, which is now represented by a denser core. Doesn't look all that dense to us, but it's very, very close, obviously. Very dense core of stars. That's the Big Dipper in the sky. So that's kind of cool. The Big Dipper and Coma Berenices are the two examples of constellations in the sky, which are not just constellation figures, but they're actually physically associated stars. So they're members of a star cluster. Okay, so this shows how the mass of a star and a planet is related to its diameter. So what this figure is showing is that if we add mass to a planet like Jupiter, what will happen is the gravity will get stronger and the planet will actually get smaller. So it will move along this track, getting smaller but yet more massive, until finally, at a point right about here, at 0.08 solar masses, you now have made the interior of the star hot enough, roughly 10 million degrees, that now hydrogen fusion will begin. And then that new energy from the core will add heat to the interior and puff out the star. And now if you add more mass, the core will burn energy faster. It will puff the star out more, and so the diameter of the star will now grow, kind of as you might more nearly expect. But initially, you can see that what happens is the mass of the object goes up while the density goes up as well, and so the object actually gets smaller. So there's low, medium, and high mass stars. So when I learned my stellar evolution, it was from Lawrence Aller, who was kind of widely regarded as the dean of stellar evolutionary theory and observation back in the 20th century. So I had the privilege of being with him during his later years at UCLA. And he was an advocate of dividing the stars into not 2 mass groupings, but 3. And I think that makes perfect sense, so that's what I'm going to do. I tried arguing that to our authors of our textbook, but they bended it all, and they decided they were just going to stick with what they got. So anyway, I think that we need 3 mass groupings. Let's talk about the evolution of these 3 mass groupings separately. So low mass stars can only burn hydrogen to helium. That's all they can do. When they've converted their mass into helium, they cannot get their cores hot enough to do any further nuclear burnings. Medium mass stars can burn hydrogen to helium, and then they can actually burn helium to make carbon, and perhaps beyond that, up to but not including iron. High mass stars, the dividing line for high mass stars is stars that are about 8 solar masses or higher, and these can fuse elements up to iron. Then when that star gets to the end of its fusion, it has a very dramatic end. It blows up as a supernova. So let's go through all that. Okay, so stars burn through their hydrogen. They evolve off the main sequence to become red giants, and then they die in various ways. Higher mass stars evolve fast. They make lots of different chemical elements as they evolve. The more mass they have, the more different chemical elements they can fuse. The lower mass stars evolve slowly. They make only helium, maybe carbon. And again, if they're medium mass stars, then they may make carbon and then up to oxygen perhaps, and a few others beyond. So stars age at very different rates depending on their mass. The more mass, the faster they evolve. Okay, so low mass stars. Again, when I use low mass stars, I'm talking about stars that only burn hydrogen into helium. So they burn hydrogen to helium. Now the helium is a denser atom than is hydrogen. So as the hydrogen turns to helium, then the core gets more dense. As it gets more dense, it's falling together under gravity. The star is tapping the second of its two inherited energy tanks, we can think of it. So a star starts out with two fuel sources. One of them is hydrogen fusion, really nuclear fusion in general, let's say. And the other is the gravitational potential energy that they inherited just from the fact that the matter is spread out initially into this interstellar cloud. Letting it fall together under gravity will release that gravitational potential energy and can heat the star. So during the star's life, it taps both of these energy sources at different rates at different times. So the helium can't burn for a low mass star. It can't get the helium hot enough. And the electrons in the center will get close enough together at a certain point that they can't get any closer. So the star can't do any more nuclear burning. It's out of nuclear fuel. And it also can't tap gravitational potential energy because the star is held up now by so-called electron degeneracy pressure. The electrons, let's just say for the moment, they refuse to get squeezed any tighter, and I'll flesh that out a little bit more later when we get to the end state of medium mass stars, when it's a little more relevant. But at that point, the outer envelope is not going to be held up because the luminosity generation is turning off. And so the outer envelope is going to move back down, and the star will contract. And as it contracts, then the outer envelope is now tapping gravitational potential energy, and so the surface of the star will heat up. And so what the star will do on the HR diagram is it will move down and to the left. Remember, to the left is hotter temperatures, and down is lower luminosities. And it will eventually come all the way over and join the white dwarfs. Those are the dead stars. Dead stars are stars that are still hot. They may be very hot, in fact, but they're no longer generating any new energy, and they're merely just cooling off. So we'll talk about white dwarfs in a little more detail later. Okay, so we talk about medium mass stars. Medium mass stars will burn hydrogen to helium. Now you've got hydrogen and helium bouncing around the core. What can you make from these? Well, you can combine hydrogen and helium and make lithium-5. So that's shown right here. But lithium-5 is extremely unstable. There's too many protons, not enough neutrons for binding, and it'll immediately fall apart. So the star's not going to gain by that. It is not going to go. You could also try combining the two heliums, and then you'd make beryllium-8. But beryllium-8 is also unstable. It's not a low energy configuration, and it will immediately fall apart as well, back into two heliums. So the only solution is for the density and the temperature to rise not a little higher, but a lot higher. Not to the 18 million degrees optimum for hydrogen burning, but to 180 million Kelvin. And at that point, you can have the two heliums combined to make beryllium-8, and the beryllium-8 lasts just barely long enough that it will be hit by yet another helium-4. And so now you've got three heliums running into each other, and that will stick because that's carbon-12. So that's 4 nucleons each. That's 2 protons, 2 neutrons, times 3. That's ordinary carbon-12. 6 protons, 6 neutrons. It's very stable, and it releases a decent amount of energy, and so this is what powers the star now as it has gotten to that point. Medium mass stars will get to this point. I'm only going to just very briefly mention this. So there are several different ways to produce helium from hydrogen. Proton-proton chain, and there's a couple of variants. depending on whether you make deuterium, like at what point you make deuterium. I'm not going to ask you to remember those details, so I'm not going to go over them. But that's one way, and that's the way that lighter mass stars, like the Sun, will primarily do. But heavier stars, which have a fair amount of nitrogen and oxygen and carbon in their core already, can go through another cycle, much more complicated, called the CNO cycle, or the CNO bicycle. And the carbon, nitrogen, and oxygen are all recycled. And what ends up happening, net at the end, is that 4 hydrogens are converted into 1 helium. So it has the same basic output. So this is a great graph. In fact, I first encountered this graph when I was taking a nuclear class, nuclear physics class, as an undergraduate, and I told the authors of our book, I said, this is a great diagram. This will really clear up for students why stars do what they do. So I think you should really include it in our textbook, and they did. So what does this show? Well, this shows the binding energy per nucleon in the nucleus of an atom for all the different atoms, from hydrogen, which is 1, all the way up to uranium, which is 92 protons. So going from hydrogen down to helium, that is a huge jump. In other words, that is extremely powerful fuel. And stars, therefore, can get away with burning it extremely frugally. They don't have to burn hydrogen very fast in order to accomplish their mission of holding themselves up against gravity. And also, since they're born mostly made of hydrogen, both of those things combine together to mean that stars burn hydrogen for almost their whole lives. And that's why when you look at just a sample of stars out there in the galaxy, you'll find that nearly all of them are burning hydrogen in their core, and that fundamental likeness of all these stars means that they all fall in a one-dimensional track across this temperature luminosity diagram that we call the HR diagram. That one-dimensional sequence we talked about, it's called the main sequence. Okay, so that's the first thing that stars do. But now see what the next 3 elements mean. So here's lithium, and here's beryllium, and here's boron, and they all have lower binding energies per nucleon. In other words, these are less tightly bound than helium. And it's another way of showing that ordinary nuclear fusion is not going to make these elements. This is not energetically favorable. So how is lithium, beryllium, and boron made? Well, the way they're primarily made is, well, out in interstellar space, the primary way in which they're made is heavier atoms get hit by cosmic rays, very powerful particles that are really the pieces of supernovae that have blown up and then been accelerated by the magnetic field of the galaxy. They're hit so violently that they basically get chewed apart, and the pieces can be lithium, beryllium, and boron. So that's where that comes from. Okay, but what stars can do is they can burn 3 of these heliums to make carbon. Okay, so 3 heliums make 1 carbon. And that's energetically favorable. That's going down on this diagram. That will release energy. It's endothermic. A star can hold itself up by doing that reaction, and that's what it does. Stars which do that are called red giants. Okay, now going to nitrogens, again, energetically unfavorable. So what ends up happening is the helium will combine, well, the carbon will combine with another helium, and that'll make oxygen, and there's oxygen. And then a beta decay will turn that into nitrogen. And I tell you what, all this nuclear physics can get really complicated and hard to remember, and I don't demand that you know that, because that's too much. We only have an hour and a half to try and get through this, so I'm going to just move forward. I'll just say that what stars can do is through alpha absorption, helium absorption, and beta decays, they can move up the nuclear fusion procedure here, and depending on how much mass you have and therefore how much temperature you can generate in your core, you can burn hydrogen to helium, helium to carbon, and to oxygen, and neon, argon, sulfur, magnesium, so forth, eventually to silicon. If you're a medium mass star, though, that's as far as you're going to get. So you cannot get to iron. I want you to notice where iron is on this diagram. It is at the very bottom. It's not the last nucleus, but it is the most tightly bound of all nuclei. So you should probably remember that. Iron is the most tightly bound of all nuclei. It's sort of the turnip of the periodic table. You can't squeeze blood out of a turnip, and you can't squeeze energy out of iron. So when a star ends up with an iron core, it's in big trouble, because it cannot do nuclear fusion to hold itself up. Only high-mass stars get to that point. Their evolution is going to be very different at that point. For medium-mass stars like the Sun, though, they will get to a point where they can't get the temperature any hotter to do these later stages of nuclear burning to generate these heavier, but still lighter than iron, chemical elements. And instead what they'll do is their nuclei, the cores rather, of the star, will get so dense, several tons per cubic inch, that the electrons are packed so tight that they refuse to get packed any tighter. Remember, electrons will repel each other. And really, it's more of a quantum effect, really. The Pauli exclusion principle comes in, and there's no more electron states in the dense core to be occupied, and so the star is held up not by ordinary gas pressure anymore. The core is not held up by gas pressure. It's held up only by what's called electron degeneracy pressure. And now the outer layers will come back in, some of them. Some will get blown back out. So these later stages of nuclear burning happen much more rapidly because the energetics, here, let's point out again. So hydrogen burning to helium is super powerful. Helium to carbon, still not bad. Carbon to oxygen, not as much. Carbon then to neon, not so great, and you can just see this line shallows out, and that means the quality, the energetic quality of your fuel is getting worse and worse. So it's kind of like going from the dragster fuel to the high octane to the low lead to the, the sawdust and then the wet sawdust, and the quality of the fuel gets to a point where finally you're trying to burn rocks like iron. So that doesn't work.